Welcome to our second lectures on applications and analysis of the switches. We have discussed till the protection parts number. Now we shall now take into considerations of the control, that is a gate driving circuits. So what does it do, gate driver circuit? It turn on and turn off the switches. So these are the design consideration. Turn power switch from off state to on state and vice versa. While transitions, power losses should be minimized, and if there is a thermal heat generation, that should be evacuated. So minimum power on turn on time through via active region where power dissipation is large, provide adequate driver power to keep power on the switch on state in case of the MOSFETs and other devices. Turn power switch from on state to off state to minimize turn off time through which the active region where power dissipation is large. Provide bias to ensure that power switch remains off. Third entity is that control power switch to protect when over voltage, over current or any unnecessary phenomena comes are sensed. Signal processing circuits which generates the logic control, and control is not considered a part of the device circuit. Drive circuit amplifies control signal to the level required to drive. Power switch. Drive circuit has significant power capability compared to logic level signals processing circuits. Provide electrical isolations where needed between the power switch and logic level signal processing and control. Drive circuit topologies. Output signal polarity, it can be unipolar or bipolar. Some driver circuit require plus minus some voltages, mostly in IGBT require a bipolar supply. So, and the bipolar polarity, signals can be bipolar or the unipolar. And we require to have a different kind of coupling, it can be DC coupling or AC coupling, connected in shunt on series power switches. Thereafter, provision for the power switch protections once it is over current, like in case of the IGBT we sense that VCE voltages, if VCE voltages is actually comes down to a certain value, then gate pulse is withdrawn. Blanking time for the bridge circuit drive, so we can ensure that there is no actually short circuit among the legs in case of the inverter drives. Output current magnitude, large on current, shorten turn on time, but lengthen the turn off delay time. This is one of the requirement. Large off shorten turn off time, but lengthen the turn on delay. These are the contradictory features, and we have to optimize these features while designing. Wave shaping to improve the switch performance. Control DIDT for BJT turn off. So, you have to see that actually base current of this BJT is actually within a control. Anti-saturations diodes for the BJT drives. So, we have to ensure that it does not go to the saturation region, then gate loses its control. We want that actually all the device to operate in a active region, especially BJT, otherwise gate loses its control. Speed up capacitors, so it will make the turn on faster. Capacitor is something like electrical mass, so we have to, or electrical inertia, so we have to take control over it. Front approach or back approach current, that is also something we have to take care of. Components layout to minimize the stray inductance and the shielding of the switching noise. This is very important while designing it. So, we have a stray inductances into the PCB, printed circuit board. We have to have such a PCB design that stray inductance will reduce, otherwise you will have a problem of high frequency. because it will act as a low pass filter and it will truncate some portion of your frequency, and it will also sometime leads to give some unwanted noise into the system. Apart from in digital system, limit cycle oscillation and all those nasty feature may come. Now let us take an example of the thyristor gate drive circuits. So here we have a zero crossing detector. From there we have analog control, and then from there we will have a pulse amplifier, and pulse amplifier will have a isolation because it is a high voltage. For this reason we require galvanic isolation between gate driver and the thyristor power circuit, and this isolation is provided by this isolation transformer. Mostly this is called pulse transformer. So pulse transformer is been shown here. This is the features. Once actually it has been pulsed, so current will flow through it, and this will be turned on. Once this MOSFET is turned on, so current will flow, and ultimately current will flow in this direction and it will turn on the thyristors. So generally power dissipations will be in pulsed. So and this core of this pulse transformation is ferrite for very good power linkage and for the highest switching frequencies. So what happen, this is a line voltage and we require to delay by alpha. So alpha delay been actually done by shifting this DC voltage. So the moment it cuts, so this will be the delay alpha, and at that point actually it will be trigger. So we got a actually high pulses, and these high pulses will actually give fed to the pulse amplifier. Pulse amplifier will generate necessary triggering pulses. Now let us come to the GTO driving circuit. Simplest driving circuit, of course we have a different kind of pulse triggering circuits, and you can have a thyristors with the UJT for different device itself was actually used and invented for the triggering thyristors. But anyway, ramp based thyristors triggering is quite useful and it has been used in practice for a long time. So we can refer to the book of the another methods of the thyristors. Of course, you can go into the actually vivid discussions of all the circuits of the thyristors, because lack of time we cannot do that. So GTO gate drive circuit has to fulfill few functions apart from the thyristors, because there is a issue of turn it off. Turn on the GTO means that high current from the current pulse, maintains conduction through the provision of the continuous gate current, and there is a continuous power dissipation, because unlike the thyristors, once it is triggered it is finished. We require to maintain little bit of gate current to make it on, GTO make it on, and turn off of the GTO with a large negative gate current pulse, that is also a requirement of the GTO. So it has quite complex gate triggering features compared to the thyristors, and reinforced blocking state by the device by a small negative gate voltage. So ultimately it can be for the HVDC applications. So and for this reason we require an isolation from this gate driver part and where the operator is operating and the high voltage sides. For this we can have a optical fiber cable or any isolations, microwave. Optical to the electrical conversion will be done, there will be a control logic, and this is basically the high frequency DC to AC conversion. So you have a high frequency transformer. This high frequency transformer used for its compactness. Once we go for the highest switching frequency, size of the device will be less, since you know that actually V equal to 4.44 for FBN into. So this what happen, if frequency becomes higher, then basically you can sustain higher rating with a low voltage, because into A will come. So ultimately B is something is constant. So if you increase the frequency, then size of the A can be reduced. For this reason we go for the higher switching frequency to reduce the size of the core, and we have a high frequency AC to the DC rectifier. Then we have a output stage, and there actually you got a GTO. How GTO is triggered? So, this is the supply of the GTO, and it has been triggered by the two MOSFETs connected in this fashions. So, once it is on, so upper MOSFET is triggered. So, then what happen? It will give to the forward pulses to it. Once it is required to be off, then lower MOSFET is triggered, and please understand that it is given a bipolar voltage. So, high negative gate current is required to be applied, followed by a little bit of negative gate voltage. So, make it off state. So, this is achieved by these features. However, current carrying capability of these devices required to be higher, and sometime instead of this thyristor we use IGBTs. MOSFET gate driver circuits. MOSFET is quite versatile device for the low voltage high frequency applications. MOSFET being a voltage control device does not require a continuous gate current to keep it on state, and since it is an insulated gate, so gate current is quite low and power dissipation in the circuit MOSFET circuit is quite low compared to the GTO. However, required to charge and discharge the gates and source and the drain capacitor in each switching operation. So, every time the capacitor across gate and source, that is CGS, has to be filled by the charges fed from the gate drive. The switching time of the MOSFET is essential, depends on the charging and the discharging time of the capacitor. So, it will turn on when CGS is filled, and it will totally discharge and have a forward blocking capability when this capacitors will be fully discharged. Therefore, first charging and discharging of the MOSFET is desired, fast switching frequency and higher current handling capability of the gate driver for this reason to operate in a high frequency. So, this is one of the small example of the gate driver circuits of the MOSFETs. It comes with a package. So, this is the MOSFETs, this has been shown as a switch. So, this is the drain and this is the source of the MOSFET, and it comes with the body diode, and upper one is the gate. So, what happen, actually you have actually the connector, from connector you have a SPDT, that is single port double throw switch. So, from there you can actually control. So, this is the external control of the pulses, and you have a buffer. That buffer will ensure that no loading takes place of this external circuit. Otherwise, this current is so small that if you have a resistance and all those things, then it cannot support the loading of this current. From this buffer actually you have a port, from port you got an LED. So, that will ensure that actually we get a pulses. From pulses we have a PWM modulators. So, that will actually generate the PWM by sine triangle comparison. From sine triangle comparison, that will go to the driver, and driver will actually drive the circuit. Let us see what is actually happens to all these blocks in one by one. Essentially, one aspect is that gate driver circuit with the integrated bipolar transistors. So, what happen? You got an NPN transistors. Once we have a pulses, we have a inverting logic. So, what happen if this pulses is on, then this transistor will go off and this will go on. So, what happen essentially, when it is on, then actually the current, then this device will get a high voltage and it will turn on, and you will have a very small resistance to turn it off to dissipate the power drop across this gate. So, that this is basically the gate resistance, and to block actually the high DVDT you have a blocking capacitors, and we have a very fast or Schottky diode. So, that we require a very fast recovery. So, for this reason we will prefer a Schottky diode or a ultra fast diode for this purpose. Now, this is one of the configuration gate driver or integrated bipolar transistors. Simplified version is definitely the totem pole configuration here that we same is used. So, you have a RB, you got a totem pole configuration. So, this configuration is called totem pole configuration, and you have a resistance to block the current through this actually these transistors, and once it gets pulse upper thyristors is on, then actually MOSFET is turning on depending on the RG and the CGS. So, this will be the RC time constant of the devices, and mind it, actually we have to provide, if it is a huge distance, that leads to the stay inductance of this gate driver circuit, and that will pose threat on noise, also high frequency application. So, this distance should be as close as possible. For this we have a modular time entities that will reduce the switches. So, discrete component definitely will give to a stay inductances. So, and also while turning off, we want that actually to bypass this resistance. So, we have a fast turn it off, and for this we turn it off by this diode, that is a very fast recovery diode we use. And so, once it is turning off, it actually current flows to the lower transistors, and little bit of negative biasing may be preferred to take it to the offset. So, this is the one of the way to do that. Otherwise, you may have it is a N type. If you have a P type, it is level shifted P type MOSFET driver is used. So, MOSFET driver P type is turned on by the negative voltage. For this we require to be actually, even though you have positive pulses, then this kind of configuration is used to use the MOSFET driver with the P channel. And for this in here, what we will find that actually this is the N channel MOSFET. So, this is actually NPN transistor, this is a PNP transistors, and you have this actually this configurations. Once you get a pulse, this NPN transistors becomes on. Once it is on, then basically then this voltage becomes 0, automatically this voltage goes low. This will be in a conduction mode, ultimately negative pulses or a 0 pulses will be applied to it, and it will come to the conduction mode. So, we have a different kind of configuration depending on a different kind of requirement. So, you can see that if you have a pulses and if you have this N channel MOSFETs, and this kind of configuration after RG you can provide to have a faster conduction. What happens while turning on, path will be through it, while turning off, so it can go through this. So, what happen actually, you can ensure that faster turn of operation by putting this whatever we have put it optional, that will leads to the faster turn off, because turn off, if you have mentioned in the data sheet in 2 class earlier, you will see that is the biggest challenge. So, we require to faster turn off by this kind of applications. Another aspects comes into the pictures, bootstrapping. This issue comes when once we require to, once actually this MOSFET is turning on, then what should be the level of the voltage. Once if it is inverter leg, lower MOSFET does not have that problem. Once it is turning on, so that voltage of this drain goes to 0, and thus and source is always 0, but reverse happens for the upper MOSFETs. But or any kind of application when you are triggered that the voltage goes to the plus VCC, then what happens, then gate voltage is lower than the actually the source voltage, then the no voltage, then actually the voltage polarity reverse in VGS, and thus it will find difficulty to turn it on that MOSFET when this condition is fulfilled. So, for this reason we require to do some kind of modification into the circuit, and we provide a capacitor that is called bootstrapping capacitor, and this method is called the bootstrapping. Principle is same, but we have a level shifting entities. This level shifting entity will ensure that actually, and this is a high voltage side or the high driver side of the devices, and ultimately it will give a pulse. Once it will give a pulse, this capacitor basically come into the picture between the driver and this actually VIN, since it is short. So, this voltage and this voltage will be same, and this voltage and this within this voltage there is a capacitor. So, what happened then due to this actually capacitor, so there will be a voltage across this point and this point, and this voltage required to be, this voltage actually maintain the higher driver voltage than this actually VIN. Actually gate voltage required to be little higher than the source voltage is fulfilled, and this kind of actually this is called bootstrapping, and it is required for the switching on the upper MOSFET in inverter or any kind of application when you turn it on these devices and the source takes the voltage of the forward voltage, and which is more than the gate voltage of the source. Now, let us come to the IGBT. IGBT is a very important features, but it requires a bipolar power supply. That is one of the difference with the MOSFETs. So, what happened, applying maximum permissible VG during the turn on period, apply a negative voltage during the turn off period, control DIDT during the turn on and turn off, and excessive electromagnetic interference, and that will cause this. Control of DVDT during the switching off, and to avoid the latch up, minimizes the switching losses and provide protection against the short circuit and fall. These are the requirements. So, now this is the example of the IGBT circuit. So, you got a logic pulses and you require a optical isolations, and this is called optocoupler, and you have to choose the frequency of the optocoupler accordingly, and once we will get a pulse we have a level shifter or comparator. So, you will shift that level and ultimately fit to the totem pole configuration. It is the same thing for the MOSFETs, but here you require a bipolar supply. You have to be plus minus 15 volt or anything whatever required, and this value of the RG should be very small, otherwise it will slow the process. So, this is the totem pole configurations, and accordingly it will turn it on the IGBT. So, the gate equivalent of it is basically this. This is VGG plus R, this is basically RB by beta 1, where beta 1 is the current gain of the IGBT. So, this is the circuits come into the pictures, and once you want to off it, so negative voltage comes into the picture. So, this becomes off and this becomes on, and ultimately negative voltage applied to the system, and thus what happened, this voltage become negative. So, this becomes the circuit. So, extra trap charges will come and will dissipate. So, this is the gate driver circuits for the IGBT. Now, let us consider the generic switching converters. We want to send power to this point to this point, and in different kind of applications we will find a different switches on. You see that S1 is connected between this pole and this port. It can be a simple SPST switch, single pole single source switch, and it can be a mechanical switch. So, let us realize it in that way, then we shall replace it by the different switches that we have discussing, power switches. So, this switch is S0, this switch is S3, and this is S4, and this switch is S2. So, let us see that what kind of switches comes into the picture, rectifier, inversion, and different kind of operation. Now, let us take state 0. What is state 0? S0 is on, that means this switch is closed, and other switches are off, and results output voltage equal to 0. This is basically the free wheel action, and it is called free wheel action in power electronics. Next, state 1, where actually load gets some power from the source. State 1, S1 and S2 is on. Let us again see, S1 and S2 are on. So, these are closed. So, power will flow like this, and it results, since there is no losses across the switches. So, V 0 equal to V in. So, you can take if you wish to have a chopper operation. So, you are bucking, sometime you may choose the state 0 and sometime will choose 1. Once you take a state 1, output voltage should be equal to input voltage, and once you take a state 0, so output voltage should be equal to 0, neglecting the diode drop because it free will is essentially a diode, but is it a switch, so it is 0. And assume B equal to 1, S1 and S2 is on, so B equal to 0 otherwise, and state 2 is, it is S3 and S4 is on, other switch is off. So, and you get the reverse voltage, that is basically minus V. So, let us see what happened. So, for the AC to DC conversion, this is the state 1 and state 2, and this is uncontrolled operation. So, what kind of switch will operate? Now, in this case what will happen, you will get the same thing in 0 and 1 is operated, but this kind of operation, you know, when it is 0, it is not getting any load. So, it will have a free will action, so you will get 0 voltage. Once you have connected this state 1, you get this part of the voltage. So, depending on your application, you will get a different kind of voltages. Now, let us take an example that you have a constant DC supply and you have chosen the state 0 and 1, 0 and 1. So, that is just chopping operation, and you have taking a time out. So, once it is input is connected 1, once it is not connected it is 0, and so on, like that it will continue. And so, this is the inversion operation if you choose 1 and 2. So, once you choose the switch S1 and S2, you get 1 and you get minus once you choose the 3 and 4. So, thus it is a inversion operation. So, from same circuit we can realize a different kind of operation with simply SPST switches. So, now we can have to go back and ultimately implement the actual switches. So, what happened then? So, if you have this kind of chopping waveform in PWM, so it is 0, it is 1, this is 0, this is actually 2, again 0, and so on, this will continue. And same way, this is an example of the AC to AC conversion. That is, it is one of the important feature nowadays coming into the pictures with the advent of the IGBT. So, we call it as matrix converter. So, these can convert AC to AC. So, accordingly you can choose a different kind of states and different voltages can be generated. So, this is directly AC to AC conversion, DC to AC conversion. Now, this is a matrix converter. What matrix converter do? We have to realize it, the switching matrix, so that it gives you direct AC to AC conversion. Otherwise, it is possible to convert AC to DC, thereafter DC to AC. So, if you wish to have a direct, there is a different way to convert it. So, AC to AC, one variable AC to fixed AC and vice versa. So, we require some kind of thing called matrix converter. We shall discuss in later how it has been realized and practiced. So, this is the combination. So, you have a M input. So, you have studied into the digital electronics, basically FPGA or PLA, this same logic has been incorporated here. You can actually close different kind of switch in a different way, and ultimately you can have a combinations of the voltages. Please understand now you have it, it is not necessarily power electronics, we talk about 3 phases voltages, but now we have a multi-phase voltages also. Multi-phase means 5 phase, 7 phase, these machines also nowadays used for the special kind of machines. So, there matrix converter heavily fit to it. So, we shall, this is actually some part of our discussion regarding analysis and gate driver protections, so that student may find it is useful for the future course of studies. Thank you very much for your attentions. We shall look forward for your next class with the devices. Thank you.